right, so in lecture 21.5, I showed you sort of a classification of boundary conditions. And we talked about, let's say, Dirichlet conditions, Neumann conditions, Robin conditions. We talked about, let's say, which ones of these enter the strong, or what we call strong conditions, which ones are called natural conditions. So these are the ones that go into the bilinear form. And so what I would like to show you today in this lecture is the, let's say, easier of the two cases between the Neumann and the Dirichlet cases, namely which the Neumann case is easier because it goes into the bilinear form. So let's say it's not easier for you to program, but it was a lot easier for me to program because the functions that deal with Dirichlet boundary conditions are very complicated. So I'll show you in this lecture how we implement Neumann boundary conditions and then Robin boundary conditions in practice, how this looks like. And then in the next lecture, I'll come back and I'll show you, let's say, the mathematical technology that's behind Dirichlet boundary conditions, which is a lot more difficult to understand. And so I wanted to deal with the Neumann case first. So this is lecture 21.5 about how to deal with Neumann boundary conditions. And if you understand Neumann boundary conditions, you also understand Robin boundary conditions. So I'm going to show you both. Okay, so just as a to pick a model problem. Okay, so I'm going to look at the Laplace equation minus Laplace u equals f, and then I have du over dn, so that would be the normal component of the gradient, n dot gradient u equals h on the entire boundary. This turns out to be a spectacularly bad example problem because it has no unique solution. And it's easy to see why it doesn't, because if you have a solution u of these equations, then actually every solution u to which you add any constant c is also a solution, because all that appears in this equation are derivatives of u here and derivatives of u here. And so if you add a constant to it, it doesn't make any difference to the derivative, of course. So if you have one solution, you immediately have infinitely many. And so this violates something that we call the well-posedness of problems. It was originally defined by Hadamard, maybe 100 and some years ago. So he says that problems are well-posed if a solution exists, which it does in this case, if it is unique, and if it is stable. And with stable, he means, so if you consider, let's say, the solution that corresponds to a function f1 and h1 on the right-hand side, and then you could consider the corresponding solution u2 that would correspond to an f2 and h2, what you would like to have is that if these f1 and f2 and h1 and h2 are just small perturbations of each other, you would like that the solutions are also just small perturbations of each other. So you would like to have something where the difference between the solutions u1 and u2 is bounded by the difference between f1 and f2 and h1 and h2, possibly with some coefficient or some constant in front of here. And you would have to define which norm exactly you want to take on the left and on the right-hand side, but in the end you want some statement like this, where a small perturbation in f or h leads to only a small perturbation of u. Now, in this case, for the Laplace equation with pure Neumann boundary conditions, it's already the uniqueness that's violated. Okay, so we don't even need to consider stability, but that's sort of the three things that we want from every solution. So instead of looking at this problem, let me just modify it a little bit. And we call this the Helmholtz equation, which has a term that is proportional to u and a term that is proportional to minus Laplace u. And in general, of course, you would want to have coefficients here just because, for example, the physical units don't match, right? So the Laplacian is 1 over, so it's d over dx squared, so it has units 1 over length squared. So we would need something over here in front of the u that also has units 1 over length squared, but let's assume that we just that thing is, let's say, 1 over meter squared. Yeah. So let me just forget about this. As a mathematician, I'm allowed to do these things every once in a while, but as a physicist, of course, I would have to say that there needs to be a coefficient. Anyway, so if I start with this equation, now you see that there's there's a term here that does change if I add or subtract a constant to the solution, and it turns out that the Helmholtz equation has a unique solution. So everything is fine here. So we do, as we always do, we multiply this equation with a test function v, and then we integrate by parts. And so this term up here gets me a v times u. This is this here. I integrate by parts, so I get plus grad v grad u, and I get a boundary term. Okay, so minus v times n dot gradient u on the boundary gamma. Okay, and conveniently, of course, n dot gradient u, this thing is exactly this thing here. So this equals h. That's not a coincidence, of course, right? This is exactly the sort of natural boundary condition that I can pose for this sort of equation. So it is not a coincidence that I choose this kind of boundary condition and not, let's say, the tangential derivative. So what I do is I'm going to replace this thing here by h, and then it becomes just v times h. There's no solution, so it goes on the right-hand side. Of course, this should not be equal to 0 here. This needs to disappear later in the slides that I've posted. So it goes on the right-hand side, and what I get is v times u plus grad v times grad u equals v times f plus v times h on the boundary. Okay, so that's going to be my weak formulation of the problem. So if I want to discretize this, I start from this weak formulation. I, as always, substitute my discrete solution. So UH is the sum of coefficients times my shape functions. I'm going to take this form, put this in here and in here. I'm going to pull the sum and these coefficients out, and what I get is the sum over j phi I times phi j plus grad phi I times grad phi j. That's going to be my matrix Aij times the coefficients uj, and on the right-hand side I have phi I times f plus phi I times h on the boundary. Okay, so that's a boundary integral here, and that's what I'm going to call fi. So that's the usual linear system. Au equals f. You see immediately that this matrix here is, for example, positive definite, because this term is positive definite. This one here is positive semi-definite. It's also symmetric because I can exchange I and j, and the whole thing stays what it is. So I get a nice symmetric and positive definite linear system here. So let me look at these Aij's and Fi's in more detail. So Aij is a domain integral plus a domain integral. So I can do as I always do, I split this over the cells, and then I compute them on the cell. So this is going to be my cell matrix, and then I'm going to copy this into the global matrix at the end of the integration on every cell. And down here for this Fi, I have the same thing. So I have a domain integral of phi I times f. But then I have a boundary integral, and the way I will write this in practice is that in the sum over all of the cells, I will loop over all of the faces of the cell. Okay, I will ask, is this particular cell on the boundary? And if the face of the cell is on the boundary, then I'm going to compute this integral here. Okay, and that's now going to be an integral over an edge in 2D or a quad in 3D. Okay. So I could show you how to do this, or how this is done in step 6, but I think it actually turns out to be instructive if I show you how, let's say, how I go about implementing these sort of things. So I often find that when I show my students how I implement stuff, they actually learn more from that than if they see how it is already done in a finished product. So I'm going to make an experiment here. I'm just going to do programming in front of a video camera, which almost never works, but we will find out if this is a good idea or not. So let me go here to my Eclipse. I've already set up a project for step 6 in the same way as I've shown you in lecture 8.01. Okay, so I'm going to open step 6. This is how it comes out of the box. I have set up all of the makefile targets, or actually CMake has done this for me. So I'm going to strip the comments here. Okay, and I'm going to get the plain program with no comments. I do this because it's a lot easier to read now. So let me hide this for a moment. So where I need to go is clearly the assemble system function. Actually, there's maybe a place before that. So in the setup system function, there is a place where we call the where we interpolate the boundary values. Okay, so we interpolate 0 boundary values on every part of the boundary that is marked with indicator 0. And if I wanted to have Neumann boundary conditions all around, this thing here clearly needs to go. So I mark this, I say control slash, and it automatically comments this out. Okay, so now there are no more directly boundary conditions. So assemble system is clearly the place to go. So let me say control O. That should give me an outline. I want to go to assemble system. Okay, so here we are. So I need to go through essentially the same kind of steps that I do when I integrate on a cell, except this time I need to integrate on a face. And the way this works is that, well, instead of a quadrature formula in dim dimensions, that's for a cell, I need something that I can use for a face. Okay, so I'm going to create a dim minus 1 dimensional quadrature formula for faces. Okay, and then I need something that allows me to evaluate the shape functions at the quadrature points on faces. And the correct class for this is not FE values, but FE face values. Okay, I'm going to create this object FE face values here. So I need, as a quadrature formula, I need obviously the face quadrature formula, and then this. So here's my list of things that I want this FE face values to compute on every face that I'm going to visit. Right now it lists the values, the gradients, the quadrature points, and the JXW value. So that's something like the DX. Now, if you go back to the slide, you see that on these faces, I really only need the values. I don't need the gradients. Okay, but I will need the quadrature points to evaluate H, and I will need to have the DX for the integral. So what I can do is I can get rid of this update gradients here. Okay, so this is that part. Now, in this loop over all of the cells here, this is where I needed to loop also over the faces of the cell and figure out whether they sit on the boundary. So I'm going to do this. So I'm going to have a loop for unsigned int f equals 0. F will be the number of the face, f less than geometry info dim faces per cell. Okay, plus f. So I need to ask, is face number f on the boundary? So if cell face f at boundary, okay, then I need to do the integral there. So now I can basically copy what I do here when I compute the right-hand side. So I see that step 6 has this coefficient in there. Let me get rid of this because the model problem that I showed you doesn't have a coefficient, so I'm just going to get rid of this. It's not really material to this. So I'm going to compute additions to the right-hand side. So I already set it to 0 for this cell here. I don't need to set it to 0 again. So I'm just going to copy this whole part here and then show you what I need to modify. So of course I need to modify this part because I need to initialize my FE face values. Okay, and FE face values wants to know not just the cell but also the face that you want to loop over. Okay, and then I loop over the quadrature points, and the quadrature points are now not just the quadrature points of the cell quadrature, but it's in fact the quadrature points of the face quadrature. So I will need to change this here. Let me hit F3 to see the place where I declare this. Okay, so this is, well, I haven't re-indexed it yet, so I'm going to just declare a new variable in face q points, and this is going to be face quadrature formula.size. Okay, that's how I called it, I think. Yes, I see. To re-index, I need to save it. So if I say Control S, it will re-index it, and then it will eventually learn after some time about phase quadrature formula. I hope so. Now, where did my FE phase values go? That's a good question. What happened here? Okay, let's try this again. We do this quick. Phase quadrature formula. Okay, this is something that I'm not particularly happy about with Eclipse, but I don't know what happened here. Anyway, so so now it knows phase quadrature formula. Okay, I want to get rid of the coefficients again. So this here. Okay, then 4 unsigned int f equals 0, f less than geometry info dim faces per cell plus plus f. If cell face f at boundary, then now we can copy this here again. Okay, fe face values dot reinit f. So instead of looping over the quadrature points of the cell quadrature, we need to loop over the quadrature points of the phase quadrature. Okay, I still need to, if you look at the formula, I still need all of the shape functions, not just the ones that happen to be defined on the face, or let's say the ones that are whose interpolation points are at the face. I really need all of those on the cell. Okay, so all i's, I don't need the loop, I'm not adding anything to the cell matrix. So what I need here is fe face values I q index, okay, fe face values dot jxw, and then what is the h, right? So this is going to be this factor h here, and let me for simplicity just assume that this is, I don't know, let's choose 10, okay? So this is really all that I need to add to this. Yes, this is really all that needs to be added to step 6. Okay, so I'm going to save this. Then I'm going to go back here. So I'm going to say make all, so that compiles. Okay, I can see how it compiles over here in the console. So let's see if I get this right, or if I get a compiler error. Okay, I do get a compiler error. Let's see if we can address this here. So, should not take particularly long. Okay, so line 210, what is it not like? No matching function for fe face values. FEQ. That's right. It needs a it needs a quadrature of size dim minus 1. Okay, so it needs the phase quadrature. Okay, what were the other errors? Probably everything followed from this. Yeah. Okay, so let's say make all. Okay. Yes, here in 248, what it should be is faces per cell. Okay, so save, make all. I want to play with one other aspect real quick. Oh, I see what the problem was here. Let's close this one here. No. This is why it got into trouble earlier on, because I had the same file open twice. And I saved the old one instead of the new one. Okay, so this one here seems to be happy. If you go to, let me minimize this. If you go to the run function of this program here, then you will find that it runs through 8 cycles. Let me reduce this to 4, okay, because we don't want to wait that long. And instead of outputting things in EPS format, I would like to use visit. And so that should be in, let's say, VTK file or VTU, either is fine. Okay, so I'm going to save this here. All of the EPS stuff can go away. Okay, so compile all. And if this works, I'm going to run it. And in the meantime, I'm already going to start visit here in the background. Okay, so Eclipse still compiling. Actually, not Eclipse compiling, but Eclipse calling the compiler that is still doing it. Okay, so it is linking now. It finished, so it's all happy. Now let me run it. Okay, so make run here. It should run 4 refinement levels. That was quick. Okay, and so what I should have gotten out of this is a file, final solution.vtk. Now let us inspect this to see if that really matches our expectations. So open final solution.vtk. Okay, add. So I'm going to show a pseudo color plot of this. Okay, draw. So this is how the solution looks like. There's a square in the middle. That's probably from the mesh. Let's look at this too. Yes, so the solution is refined only towards the boundary. Well, that's maybe a little bit of a 2-coarse mesh. So let's run this again. So I'm going to say, in the beginning, I'm just going to refine 4 times so that we get a better solution here. So I'm going to say make run. Make run will automatically make sure that the program is compiled as well. And in the meantime, I'm going to keep working here on my Eclipse. So if I choose add, I want to add an operator. I want to elevate it into the third direction. So if you're not familiar with this, there's a whole lecture on visit somewhere on my website. So transforms elevate. Okay, and then I need to say elevate by what? So transform elevate. I want to elevate by the solution. So I want to show the solution as a 3-dimensional one. Okay, so apply, draw, dismiss. So this is how the solution looks like. Okay. So how far did Eclipse get down here? So it is still running. Okay, should not take much longer, hopefully. Okay, there it goes. So in Eclipse now I can reopen. Okay, you see that the mesh is much finer now. Okay, so this is how the solution looks like. Now, this is a good question. Why exactly does it not show the correct normal values? Okay, so you see that, or maybe you don't. So the minimum value is 0, the maximum is 0.25. I have a suspicion why that is. So let me make this a little bit faster and go back down to 3 here. In my save accident, I also overwrote the change that removes the interpolation of Dirichlet boundary value. So I need to go back to setup system and remove this part again. So Control/ to save, make run. So you this is not really what I wanted to show, of course, but you get to see a let's say my process of debugging. So how did I see this? Well, it has the wrong Neumann values here, right? I want the Neumann values to be +10. That's what I chose. I said that the normal derivative, so the derivative in radial direction here, should have been +10. Well, +10 means it needs to curve up on the outside, right? Or at the very least, it should. Well, you will see in a second. I know that there's going to be another mistake now. But so it should curve up, but it doesn't. But I can see that the value is 0, okay? Well, so my brain starts to think about this. Why would it be 0? That's, of course, because I forgot to eliminate the part here where I interpolate 0 boundary values. Well, if I interpolate 0 boundary values and then apply them after the computation of the right-hand side, then the Neumann values get overwritten by the Dirichlet values that I interpolate here. So that was sort of my reasoning why that reminded me that I needed to do this. Now, let's go back to here. So I got an error. It says that the solution doesn't converge. And the reason, of course, is that I still have a pure Dirichlet problem, right? A pure Laplace problem. What I needed to do is I needed to get back the term here that comes from the Helmholtz equation, okay? Right now, I only have this term. For this one, we knew that the solution is not well defined. So let's add this as well. Okay, minimize here. We'll go back down to assemble system. So the right term that I have to add to it was something like this here. So that's shape grad times shape grad. That is the Laplace part. Okay. So so I need to add a term here. So let me write this like this, okay, where I add to it the indentation is a problem. Okay, so right now I have shape here. This is what I want. So right now I have shape value times shape value plus shape grad times shape grad, okay, times the whole thing dx. That's exactly what I needed, okay? So, final attempt, it better work now. So shape values, this is my phi I at point xq times phi j at point xq. This is the gradient of phi I at xq times the gradient of phi j at xq. And with some luck, the error message will go away now. The error message said that the solution, or that the linear solver, the CG solver, did not converge, which it can't because the matrix was not positive definite. It was positive semi-definite, but it had a 0 eigenvalue. So it seems to run now. Let's see how far we get. Okay, so it's done. Let's take a look at the solution now. Okay. So reopen, hallelujah. Okay, so this seems to work. So now we see that the solution does have a certain slope that goes up here. And I mean, let's figure out if the solution could roughly be correct. So the size of my circle here, I think it has radius 1. Okay, so if this was a straight line from here to here, and I want the solution to have a slope of 10, then this point would need to be 10 units higher than this point. But in reality, it curves up a little bit, so I would expect that it's not quite 10 units higher than this point, because the slope becomes steeper as I go to the outside. So you can't see this, but the lowermost point here of the solution is 18. The highermost point is 23. Okay, so I'm willing to believe. So if it was just a cone, the slope would be 5, but because it curves up, I'm willing to believe that the slope here really is 10, which is exactly what I wanted, of course. Okay, so solution looks okay. I'm happy with this. So now that I've shown you how to do Neumann values, let me show you real quick how to do Robin type boundary conditions as well. And it's basically the same thing. So I just take the original Helmholtz equation, and the Robin boundary conditions are not du over dn equals h, but u plus du over dn equals h. I do the same thing. I multiply with a test function. I get n dot gradient u. That's this thing here, which happens to be h minus u. Okay, so I substitute this. The h, again, this needs to, it's not 0. This is the correct equality here. So the h goes to the right-hand side. It gives me this term. And the u stays on this side here, so minus and minus gives me a plus. So I get in the matrix here another term v times u on gamma. Okay, so I could show you how to do this. I mean, you get the idea, I guess, that what needs to happen in Eclipse is that I add here in my matrix. So in the assembly, right, I will have to add something here that looks roughly like this, right? So these terms here, where I get a term of shape value times shape value, but on the boundary with FA face values. That's basically all that needs to be changed. So to show you the corresponding terms, so if you substitute the solution in there, you get a term on K, on cell K, where you have an extra term where you loop over all of the faces, phi I times phi j, and F is as before. So I could show this to you, but my 30 minutes are over, and I think you got the general idea of how this works. So let's leave it at that. You just have to add the one extra loop.